Dive into the roaring depths of maritime engineering as we unveil the secret tests shaping the reliability of giant ship engines. Welcome back, folks. Today, we're delving into the extraordinary world of testing giant ship engines. Imagine the power of 1,000 car engines packed into a single colossal cargo ship engine, weighing an astonishing 2,300 times more than 13 blue whales. These mammoth engines are the unsung heroes of global trade, carrying 9 out of 10 products we use in our daily lives. So, buckle up as we explore the rigorous testing procedures that ensure these colossal engines are ready for the high seas. Engine evolution. But before we dive into testing, let's take a step back and appreciate how far ship engines have come. The days of steam engines are long gone, replaced by a progression that mirrors the advancements of maritime technology. From coal-fueled turbines to nuclear power, and ultimately to modern diesel engines, the journey has been awe-inspiring. The 1950s marked a pivotal era when marine technology catapulted forward, introducing not only new engine types but also shaping the infrastructure of giant ships inside the giant engine. Now let's unravel the mysteries concealed within the colossal engines that power the mammoth vessels dominating our oceans. The largest ship engine, crafted by AOE Works Japan's Diesel United Limited, stands as a titan at 45 feet high, housing 14 cylinders that generate a staggering 4.42 megawatts of power. Step inside this mechanical marvel, and you'll find a world where familiarity meets scale. Despite its colossal size, the inner workings mirror those of any engine, with a crankshaft orchestrating a complex dance. Picture standing within the crankcase, a space where a person can navigate a ladder to address any mechanical issues, a delicate task given the slippery surface coated in lubrication oil. Beyond its sheer size, this giant engine shares commonalities with its smaller counterparts, turning energy into motion. Yet, the scale of this process within the cavernous chambers of a 5-story building equivalent is a testament to the awe-inspiring engineering feats propelling our maritime giants across the seas. Engine propulsion. These giant engines not only defy size norms but also redefine propulsion in the maritime realm. From traditional propellers to innovative ducted propellers, jet engines and water jets, the methods of propulsion are as diverse as the ships themselves. The introduction of gas turbines, seen in vessels like the RMS Queen Mary 2, adds another layer of complexity. Most cargo ships rely on LNG or liquefied natural gas engines for everyday operations. This shift reflects the industry's commitment to cleaner and more efficient fuel sources. Picture a colossal propeller at the back, driving these ships forward at impressive speeds, consuming around 250 tons of heavy fuel oil daily. The intricacies of how these giant engines work are not just a feat of engineering. They are the heartbeat of global commerce, propelling our goods across vast oceans and connecting us in ways we often take for granted. Testing procedures. Now let's delve into the intricate and crucial testing procedures that giant ship engines must undergo before embarking on their monumental global journeys. These tests are the backbone of ensuring the reliability and efficiency of these colossal engines. 1. Manufacturer's Acceptance Test. The journey commences with the Manufacturer's Acceptance Test, a meticulous examination that takes place at the manufacturer's testbed. Here, engineers scrutinize every aspect of the engine's performance values to ensure they align precisely with the specified parameters. This initial phase is paramount, as any deviations could have profound consequences during the engine's operational life. 2. Sea Trial Test. Following a successful acceptance test, the engine transitions into the sea trial phase. This stage is a dynamic and real-world examination where the ship and its engine are put through a series of rigorous paces. The results obtained are then compared to predetermined standards outlined in the agreement. Sea trials simulate the actual conditions the engine will face during its voyages, ensuring it can perform optimally under diverse circumstances. Sea trials, the 4 phases. The sea trials consist of 4 distinct phases, each playing a crucial role in ensuring the engine's seaworthiness. Phase 1. Mooring Trial. As the ship is securely tethered to the dock, the mooring trial is conducted to assess stability and performance in a controlled environment. This phase examines the engine's response to various conditions while stationary, laying the foundation for further trials. Phase 2. Running-in Trial. With the engine's output under meticulous control, the running-in trial focuses on testing piston rings and cylinder liners. This critical phase ensures that the engine performs optimally during its initial stages, setting the tone for its long and demanding operational life. Phase 3. Preliminary Trial. Executed. Just before the grand finale, the preliminary trial involves fine-tuning the engine for optimal performance. This phase serves as the last-minute adjustment to ensure that every component is functioning seamlessly before the engine faces the ultimate test. Phase 4. Official Trial. The pinnacle of the sea trials. The official trial encompasses 11 crucial tests conducted in the open sea. From a consumption test to noise measurement, these trials rigorously evaluate the engine's capabilities, certifying its readiness for the challenges of global maritime travel. Successfully completing these tests marks the engine as seaworthy, prepared for the vast and unpredictable oceans that await. 3. Comparative testing. Once the ship is delivered to its new owner, the vessel undergoes a series of comparative tests throughout its service life. This ongoing evaluation is crucial in ensuring that the engine consistently meets and exceeds the service standards over time. Continuous monitoring and comparative analysis help identify any deviations or performance issues, allowing for prompt adjustments or modifications. 4. Research testing. Feedback from the new owner initiates the research testing phase. This stage involves a detailed examination to identify and resolve any potential issues or modifications required for optimal performance. Various testbed tests are conducted during this phase, including consumption trials, running stern trials, starting and reversing trials, and increased torque trials. These tests provide valuable insights into the engine's behavior and performance under different operational scenarios. 5. Stability testing. In the realm of maritime engineering, ensuring the stability of giant ships is paramount. Advanced computer simulations and declining experiments play a pivotal role in stability testing. These simulations allow engineers to scrutinize a ship's performance under various sea conditions, predicting its response to waves, wind, and unpredictable elements. For smaller ships, a keel is commonly employed to enhance stability, preventing capsizing. However, for these colossal vessels, stability testing goes beyond traditional measures. Innovations like Raftar Maritime's 180-degree turning boats are pushing the boundaries. By keeping the keel downward at all times, these vessels redefine stability, especially during rough seas. This technology, widely adopted by search and rescue organizations and coast guards, showcases the industry's commitment to advancing stability testing, ensuring these giants navigate the seas with unmatched resilience. Final testing measures. Before a ship is deemed seaworthy for real-world operations, it must undergo a series of final testing measures. Draft measurements are taken to assess the ship's depth in the water, ensuring it adheres to design specifications. The anchor test becomes a crucial examination of the ship's ability to anchor securely, a fundamental aspect of maritime safety. Additionally, steering gear tests simulate scenarios where the ship cannot utilize its steering gear during docking, ensuring the crew can navigate challenges effectively. The main engine endurance test, including speed trials, crash-off tests, astern running, and turning circle tests, evaluates the engine's performance under diverse conditions. Navigation equipment is scrutinized, and a blackout test is conducted, simulating a loss of power to assess the ship's preparedness for emergencies. These comprehensive final testing measures ensure that the ship is not only seaworthy, but equipped to handle the myriad challenges it may encounter during its operational life. And there you have it, the epic journey of testing giant ship engines, the powerhouses behind global trade. From the colossal engines themselves to the meticulous testing procedures ensuring their reliability, we've uncovered the fascinating world that keeps our products sailing smoothly across the oceans. If you enjoyed this video, then don't forget to like, subscribe, and hit that notification bell for more deep dives into the marvels of engineering. Thanks for watching, and until next time, fair winds and following seas.